Lesson number 14 talks about ANOVA, which is short for analysis of variance. And the items we need are the TI-83 calculator, the formula sheet for the linear regression and ANOVA, and also the F charts. So this is the same. The formula sheet is the same formula sheet that we used in last week's lesson for linear regression. So that's the top half, which we used last week. So now we're going to reference the bottom half. And what I did is I put an arrow, if you notice on the right, I put an arrow up and over because that kind of tells you which formulas you're supposed to do in what order. So we should be working on the bottom formula first, follow the arrow, and then up to this formula. Then we're going to go to the upper right for this formula, then the upper middle, and finally to the upper left. And the degree of freedom for the numerator and denominator is just part of the final analysis that we have to do. So you're just going to go 1, 2, and 3, 4, and finally 5. The letter that's used for ANOVA testing is called F. That way, if you see the letter capital F in anything, you know that analysis of variance was accomplished for the problem. So, and also the F charts. Let me see if I can grab the F charts. The F charts look like this. Again, you're gonna download these off the website, and there's 4 charts. This is a chart, if you notice in the upper right hand corner, this is for the 0.01 significance levels, or 1% significance level. And then on this part is the 2.5% significance level. And then my charts look a little different than the ones that you're going to download, but they're all identical. This one is the 0.05 or the 5%. And then finally on the bottom is the 0.10 or 10%. So depending on what alpha they have in the problem, that's the chart that you're going to reference. 1, 2.5, 5, or 10% significance level. So here's what ANOVA testing is all about. ANOVA testing, again F testing for short, because that's the letter that's used for the test statistic, is a statistical concept used to compare the means of 3 or more categories. For example, a family doctor may want to know if the mean HDL levels of cholesterol in males are the same in the age groups 20s, 30s, 40s, and 50s. So there's 4 different groups. Or a business owner may want to know if the average sales is the same or different for younger females, younger males, and older males. And again, we want to compare the means of these. So for the doctor, you would see if the means of the age groups are the same for HDL, or you would conclude that the means are different. And for this business owner, again, the means for the younger and older males and females would be either the same or they'd be different. And that's important information that you'd like to know. That sets up the null and alternate hypothesis. The hypothesis would be HO, the means of the categories are the same, the key word there being the means, or the means of the categories are not the same. Each test has a significance level alpha, which again is placed in the tail, and which separates again the accept HO from the reject HO region. And the tail region is again always reject, just like it has been all semester long. The steps are like this. And we're going to do these steps on a couple questions that are going to follow. You want to find the totals for each of the categories. We're going to call them capital T for totals. And you're going to find the totals of the first column, second column, third column, and if there's a fourth column, etc. Those are called T sub 1 for the first column, T sub 2 for the second column. And we're going to find the number of data in each category, and the number of data in each one would be N for number. So we want to know the number of the first column and second column, and etc. Once we do that, we're going to find the value for the T1 squared over N1 plus T2 squared over N2, etc. And we're going to find the N, which is the total number of data, K, the total number of categories, the summation of X, which is the sum of all the data, and the summation of X squared, which is square each piece of data separately, then sum all of them up. So these are the 5, if we can find these 5 unknown values, then we can do all of the formulas that I just showed you on the ANOVA sheet very quickly. Step 3, we're going to find all of those values on the ANOVA sheet like I just talked about, and then we're going to compare our F statistic to the critical value, and if you are not in the tail, you're going to accept. If you're in the tail, you're going to reject. Okay, so let me just leave that there for you for a second. You can pause the video, you can copy that down if you like. So let's do a few questions. Question 1, okay, says, A local branch of a bank wants to know if each of 4 tellers serves on average the same number of customers per hour. So the following table lists the number of customers each teller served during some observed hours, and we'd like to use an ANOVA test with significance level of 2.5% to see if the average customers served is the same or different for each teller. So we're looking for the averages. Are the averages the same or are the averages different? Place all working solutions on your own paper, not on this exam. Well, that'd be a question I'd put on a test, and it would be like, you know, this I copied off of an exam, so we don't have to worry about the point total. Okay, this wouldn't be worth 30 points on your final. It'd be multiple choice questions. We'll talk about that later. So here's what we need to find. We want to know, are the averages the same or are the averages different for each teller? So the first thing we have to find is we have to find the total of the first column, the total of the second column, third column, and fourth column. So we're just going to add them up. So 19 and 21 and 26 and 24 and 18. That's going to give us back 108 for the total of this first column. Total of the second column is 14 and 16 and 14 and 13 and 17 and 13. So that's 87. Third column, 11 and 14 and 21 and 13 and 16 and 18 is 93. And finally the last column, 24 and 19 and 21 and 26 and 20 is going to give us back 110. So those are the totals. Total of the first and second and third and fourth columns. Then we want to find the number of the first column, the number of data in the second column, third column, and fourth column. So we have 1, 2, 3, 4, 5 pieces of data here, 6 pieces, 6 pieces, and 5 pieces. Now we want to find 5 things. To make our formulas a little easier to find, we want to find T1 squared over N1 plus T2 squared over N2 plus there's T3 squared over N3 and then T4 squared over N4. So we're going to square the totals and divide by the number in each one of those. Okay, so here we go. So we're going to take 108 squared over 5 plus 87 squared over 6 is the total of the second column. Total of the third column is 93 squared over the number in that column, which is 6. And then the total of the fourth column is 110. We're going to square that and divide by the number in that column, which is 5. Okay, so in our calculator, 108 squared divided by 5 plus 87 squared divided by 6 plus 93 squared divided by 6 plus 110 squared divided by 5. Okay, we're getting back 7455.8. Okay. Now, next, I would like to find N. I'm going to put it here. N is the total number of data. And we had 5 here and 6 here is 11, and 6 here is 17, and 5 here is 22. So 22 is the total number of data. K is the number of categories. There was 4 tellers, so 4 categories. We need to find the summation of X. This is the sum of the data. We could either add up all of the data that's up here, or we can just make our lives easier, and we have subtotals, so we can just add up the subtotals. And so if we take 108 and 87 and 93 and 110, we get back 398. Okay, and then we have to find the summation of X squared. That's the sum of the data squared. Now that doesn't mean take the sum of the data, 398, and square it. That means square each piece of data and add them as we go. So that means we have to square each piece. 19 squared plus 21 squared plus 26 squared plus 24 squared plus 18 squared plus 14 squared plus 16 squared. And I know it sounds like a lot, but that's what we got to do. It doesn't take too long. 19 squared plus 21 squared plus 26 squared plus 24 squared plus 18 squared plus 14 squared and 16 squared and 14 squared, 13 squared, 17 squared and 13 squared plus 11 squared and 14 squared and 21 squared, 13, 16 and 18 squared, 24 and 19 and 21 and 26 and 20 squared. Okay, we're getting back 7,614. All right, so there's the 5 items I need. Doesn't matter what order you do them in, but as long as you have all 5. So we need that, that, and that. All right, so we're going to follow our formulas now. I'm going to bring the formula sheet over. Okay, so first thing it asks for is SSW, and this is the formula for SSW. Okay, so SSW asks, take the summation of x squared, subtract t1 squared over n1, plus t2 squared over n2, plus t3 squared over n3, plus dot dot dot. Okay, well, the summation of x squared we just found a second ago, that's 7,614. We're going to subtract all of these t squareds plus other t squares, and that's the one we found up here, and that's 7455.8. We're going to subtract those two numbers. 7614 minus 7455.8. 158.2. Okay. Looking at my formula sheet. Move it there. So that's the one we just did. Now we're going to do the next one, which is the SSB. The SS's stand for sum of the squares. B means between samples. This means sum of the squares within samples. I won't test you on the names, but it's just, again, a name which stands for a formula. We're just going to fill in for the values and get back a value and a number. So this is the formula for SSB. I'm going to copy it down in your notes here. So over here, we're going to say SSB is t1 squared over n1 plus t2 squared over n2 plus dot 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 minus the summation of x, the quantity squared over n. Now we already have all of these values. Okay, the t1 squares we found up here, so that's 7455.8. We're going to subtract the summation of x, the quantity squared. So we need the summation of x, which is 398. We're going to square that, and we're going to divide by n, which is the total number of data, which is 22. Okay. 7455.8 minus 398 squared divided by 22. 255.62. Okay. Following our formula sheet, so we did the bottom two following the arrow. Now we're going to jump up to MSW, which is SSW divided by n minus k, and then we're going to jump over to MSB, which is SSB divided by k minus 1, and then finally we're going to find F, which is the division of these two answers. We're going to follow those. All right, so here, scoot down just a smidge. All right, we want to find MSW. That's SSW divided by n minus k. So SSW we found to be 158.2. Okay. N is the number of data, that's 22. And k is the number of categories, which is 4. So that's going to give us 18. 158.2 divided by 18. 8.79. And then over here, we're going to find MSB. That means mean of the squares between samples, and that's found by taking SSB, sum of the squares between samples, and dividing by k minus 1. We found MSB previously to be 255.62. N is the number of categories, which is 4, minus 1, which is 3. So 255.62 divided by 3, 85.21. Okay. Finally, F, which is the variable used for ANOVA, is MSB divided by MSW. Now we just found MSB to be 85.21. We're going to divide that by MSW, which is 8.79. And in our calculators, we're going to say 85.21 divided by 8.79. 9.69 is our value for F, and that is our test statistic. Okay, that's the value that we're going to put in our chart to determine if we accept or reject HO. Now, we need to have an F distribution. If you're not sure, go back up to the original question, which is 2.5% for our significance level. So I am going to take the table that says 2.5%, and here it is. Okay, 2.5% in the tail. The distribution looks just like this with 0, and then it goes like this. So it looks similar to a one we did previously with chi-square. So we have 0 here. This is accept HO. The tail is always reject HO. We need to find this critical value so that I can determine if we accept or reject. Well, if you notice in the distribution, it says degrees of freedom for the numerator on the top, and then on the side, if you look sideways, it says degrees of freedom for the denominator. So I need those values. Well, I put those in the cheat sheet here. Okay, degree of freedom for the numerator is k minus 1, and for the denominator is n minus k. So off here on the side, degree of freedom for the numerator is k minus 1. We know k is the number of categories, which is 4. Take away 1 is 3. And then the degree of freedom for the denominator is n minus k, and we know that n, the total number of categories, is 2, and k, categories, is 4. So total number of data is 22 for n, and 4 for categories. So that gives us 18. So this is numerator, this is denominator. They usually write this as F, 3 for degree of freedom of numerator, comma 18 for denominator, comma 0.025 for the significance level asked in the question. So that's usually the way they write it. Okay, so what is the F value for this, this, and this? So we're going to look up. Okay, so degree of freedom of the numerator we found to be 3, so we're going to go to column 3. This is, again, let me put it for the 0.025 significance level table. 3 for the numerator, and we're going to go down where it says 18 right here for the denominator, and you'll notice that that is a 3.95, and that's going to go in our critical value. We have a test statistic of 9.69, and that is going to lie to the right of 3.95, which is in the tail. So we are going to conclude we reject HO. And then if we go back into our notes where we started, HO was the means are the same. H1, we're rejecting that for this question. So we're going to accept H1, which is the means of the categories are not the same. So we want to list that. So reject HO, and we're going to, as a conclusion, say means of the categories are not the same. Which basically, if we go back to the original question, we're saying that the means, or the average number of customers each teller sees in a given time period are not the same. So some tellers see more customers than others. And you can't just look at the data and say it looks that way. You have to actually prove it. So we just did, and there you go. So that's a question for F distribution. All right, so let's do another one. Like we've been doing all semester long. Okay. I'm going to show you the question, and then I think it's best for you to actually pause the video and see if you can do it yourself. So this is the stopping distance for tires was tested to see if they are different. Below is a chart representing the stopping distances for 3 different types of tires under normal driving conditions. Test with a 5% significance level to see if the stopping distances are the same. Okay, so we have 3 tires, and this would be one set of tires that stopped at that number of feet, this number of feet, and etc. This would be tire B, this would be tire C. All right, so we want to test this. All right, so the first thing we're going to do, we're going to find the totals. So we're going to find total of the first column and second column and third column. And then we need the number of the first column and second column and third column. So we're going to add up the first column, 52 and 46 and 51 and 52 and 48. We're getting back 249 for the total of that one. Second one is 47 plus 52 plus 44 plus 48 plus 50 plus 49. We're getting 290 for this one. And then for this one, 56 and 61 and 52 and 55 and 62 and 62. 348. Okay, so that's the totals of each one of the columns. We're going to figure out how many number are in each one. So 1, 2, 3, 4, 5 is the number of data in that one. We're going to have 6 data in the second one and 6 data in the third one. So that's the beginning. All right, so now we want we want 3 of the 3 columns. We want to find 5 items. We first want to find T1 squared over N1 plus T2 squared over N2 plus T3 squared over N3. So 249 squared over 5 plus 290 squared over 6 plus 348 squared over 6. .249 squared divided by 5 plus 290 squared divided by 6 plus 348 squared divided by 6. Okay. 46600.87. Okay, that's going to be an important number, so I'm going to put a red box around it. We're going to use that for a minute. Okay, we need to know N, total number of data. We have 5 and 6 is 11 and another 6 is 17 total pieces of data. We need K, the total number of categories, which is 3. The summation of X is the sum of all the data. It's easiest to just add up the subtotals of the T. So we're going to take 249 and 290 and 348. 887. And the one we have to make sure we don't make a mistake is the summation of X squared. So that again is squaring each individual piece of data, then adding them up. Don't take the data and square it. Square the data individually. So 52 squared and 46 squared and 51 squared and 52 squared and 48 squared and 47 squared, 52 squared, 44, 48, 50, and 49 squared, plus the third data set over here, 56 squared plus 61 squared plus 52 squared plus 55 squared plus 62 squared plus 62 squared. And there's all the numbers. We're getting back 4, 6, 7, 5, 7. All right, so these are all the numbers that we're going to need in order to get our answer. We're going to follow the formula sheet. Okay, again, we're going to work our way SSW up to SSB, and then we're going to find MSW to MSB, and finally to F. We're going to calculate the degree of freedom for the denominator and the numerator, so please reference this as we're going through each step. And here we go. So we're going to find SSW. That is the summation of x squared minus t1 squared over n1 plus t2 squared over n2 and t3 squared over n3. So the summation of x squared is 46757. And we're going to subtract the t1 squared over n1 and 2 and 3. That's 46600.87. Okay, so on our calculator, 46757 minus 46600.87. There we go. Okay, 156.13. Okay, that's SSW. We're going to need now SSB, sum of the squares between samples. That's t1 squared over n1 plus t2 squared over n2 plus t3 squared over n3 minus the summation of x, the quantity squared over n. So the t's is 46600.87. I'd like to subtract the summation of x, which is 887 squared over n, which is the number of data 17. 46600.87 minus 887 squared divided by 17. 320.34. Okay, that's SSB. Next up, we need MSW. That's SSW divided by n minus k. All right, we found SSW 156.13. N again is the number of data, which is 17. And we're going to subtract the number of categories 3. And that's going to give us back a total of 14 for our denominator. And we're going to take 156.13 divided by 14. 11.15. We now need MSB. That's SSB divided by k minus 1. That's according to the formula sheet, right? So SSB we found right here, 320.34. And k is the number of categories, which is 3, and take away 1, which is going to be 2. 160.17 is that value. And finally, we need the value for F. That's MSB divided by MSW. MSB we found to be 160.17, and then MSW over here we found to be 11.15. So 160.17 divided by 11.15, 14.37. So this is our test statistic. Same name given to hypothesis testing, which is also given to the chi-square value. In hypothesis testing, it was a z-score. For chi-square testing, it was a chi-square. And now for ANOVA testing, it's an F. So if we see the capital F, we know it was an ANOVA test. And now, so we're going to take this 14.37, and we're going to place it in a table. Distribution, and 0, this is accept HO, this is reject HO. The question, if I scroll up, is asking for a 5% significance level. Okay, I need a degree of freedom of the numerator and a degree of freedom of the denominator. The degree of freedom of the numerator is k minus 1, k is 3, 3 minus 1 is 2. The denominator is n minus k. We found that earlier, just a second ago. Here's n minus k right here. N is 17, k is 3, so that's going to give us back 14. So we want here the value for f for numerator 2, denominator 14, significance level of 0.05. So we're going to look up from the table. Okay, make sure you look at the one that says 5%, 0.05. And we're looking up a numerator. Again, we're going to go back, a numerator of 2 and a denominator of 14. So 0.05, the numerator is 2 on the top, and we're going to go down where it says 14 on the left-hand side. And we're getting back a value of 3.74. And that is our critical value. Knowing that, where does our f lie? 14.37 lies to the right of 3.74. So we are going to end up in the tail, which is reject HO. And again, I refer you back to the original notes where HO is the means of the categories are the same. That's what happens in ANOVA testing. That's HO. We're rejecting that, so we're accepting H1, which is the means of the categories are not the same. And so that's what our conclusion is going to be. Means of the categories are not the same. So we concluded that the average stopping times are not the same for the 3 different tires. So they stop at different lengths, significantly different lengths, because that's what we concluded. And that's how you do ANOVA testing. So make sure you do your homework. I'll leave that there. Any questions, as is true for the whole semester, please send me an email and I will try and help you further. And I hope you enjoyed the class. This is the last lesson. And good luck on the last exam. And any questions, let me know. Thank you.